Last week I talked about options for greenhouse gas emission reduction. Today I'm going to focus on the costs of doing so, and then next week I'll talk about policy instruments to bring about these emission reductions. I think the first take-home point is that the costs of emission reduction or the costs of abatement are real and they're positive. That is, it costs money. There's three ways of sort of getting the intuition there. In an unregulated environment where greenhouse gases can just be vented into the atmosphere, emissions are essentially costless. There's no burden, no nothing. You can just do whatever you want. You can emit these things without paying any price. With climate policy, and let's assume it's a tradable, it's a system of tradable permits or it's a carbon tax, you have to pay to vent those emissions into the atmosphere. So that immediately brings a cost, and that is sort of your primary signal. Another way of looking at this is mathematically. If you assume that agents are rational and they're maximizing their utility or their profit, essentially what climate policy does is it adds a constraint to that maximization process. And basic calculus will tell you that if you have an optimization problem and you add a constraint and that constraint bites, that is, it is a real constraint, then that drives down your utility, that drives up your costs. That's a mathematical truism. And third way of making this intuitive is that essentially what climate policy does is it forces you to use different energy than you otherwise would have done. So it forces you to switch from coal in power generation, which is about 4 pence per kilowatt hour, to use wind instead, which costs about 8 pence per kilowatt hour. So that doubles roughly the cost of the electricity, and of course that brings a cost. So those are three basic intuitions that if you intervene in the economy, you force people to use energy more efficiently than they otherwise would have had, or use different energy than they otherwise would have done, then you must incur a cost. There are a good few people out there who are terribly confused about this, and this goes back to the graph I showed last week, where because energy is a cost, it is in everybody's interest to save energy. So there is this process of technological progress in the background, where energy efficiency always improves. But what we need to do in climate policy is not claim victory, ascribe to policy what the market does in and of itself. No, we should accelerate the rate of energy efficiency improvement, and we should accelerate the rates of switching of fossil intensive to fossil extensive energy. Right? First principles are very simple. Emission reduction costs money. Exactly how much depends on a large number of things. What you're looking at here is a key result of EMF 22. That's the Stanford Energy Modeling Forum, which is a group of academics who come together and then sort of run their individual models under controlled circumstances and see at what points do the models agree with one another and at what points do they disagree with one another. And there's an awful lot of information on this table, and the numbers are terribly small. But So let me take you through it. Here we have the 10 or so different models that took part in this exercise. Here we have alternative scenarios where this is a fairly lenient target for global climate policy over the century. This is a more stringent target, and this is an even more stringent target. So this is essentially at what level do we want to stabilize the climate. This is about 2 degrees, this is about 3 degrees, this may be more towards 4 degrees warming since pre-industrial. Coming. Two sub-targets or two sub-policies. Here we have every country enthusiastically embracing climate policy around the year 2015. Here we say only the rich countries do so and poorer countries come in later. And then we have two further divisions. Do we approach the target from below? Do we always stay below this particular concentration of greenhouse gases, or are we allowed to go over first and come down later? So that's all the information that is in this table. It immediately tells you that the question, what will climate policy cost, is just not a meaningful question, because climate policy is not defined. It's just not precise enough. You can do climate policy in many different ways. You can have many different targets. You can approach this in an infinite number of ways, not just the 10 that are listed here. The costs here are measured in trillions of dollars, which is large compared to your bank account. The size of the world economy is actually measured in tens of trillions of dollars. So in that sense, these are relatively small numbers, and the numbers that you see here is the net present value over the century. So we are talking about a small fraction of the total economy. If you look at sort of the first column here, then what we see is that some models say climate policy, specified here, will cost about $20 trillion. Other models say, no, it's more like $2 trillion. And that is the second main point of this table. We are talking about what is the cost of future policy. So you would expect a large range of uncertainty, right? And the range of uncertainty is about an order of magnitude. Models say, well, it can be 10 or it can be 20. Sorry, it can be 2 or it can be 20, right? That's a large range of uncertainty. And there's also a bit of a problem in this literature, and that is that everybody, almost everybody, is running forward models. We're always looking at the future. It sort of goes back to the early days of climate economics, where climate policy was something of the future, and the only thing you could do was use prospective models, ex ante. But the literature sort of got into the habit that this is what we do in this literature, and we seem not to have noticed that over the last 20 years there has been a good bit of climate policy around the world, and we could actually test these models, say which one did better. That is a rare exercise. So for the moment, we just have to live with alternative models, all pretending to be equally good, giving a wide range of results. Third thing we take away from this table is that if you move to a more stringent target, the costs go up. No surprise there, right? So if you take this particular model for 650, the cost is 13 trillion. Then go to the equivalent. For 550, the cost go up to from 13 to 30. And then you go to 450, it goes up to 125. So costs accelerate very, very rapidly if the target becomes more stringent. And that's also what you should expect. If you compare this column to this column, these columns to these columns, this column to this column, then what you see is that if the whole world enthusiastically reduces its emissions, then the costs are, say, 13. But if the poorer part of the world say, no, 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 you guys go first, we'll come in 2035 or in 2050 or so, then the costs go up. Again, that should be intuitive, right? You have a global target. If half of the world says, you guys solve it, then obviously you impose a higher cost fee because you exclude a lot of options for greenhouse gas emission reduction. You exclude a lot of cheap options. Final methods in this table, and that is all this stuff that is going on here. You see is that if you move to the right in the table, then you see all these crosses appear. And that means that the modelers asked their model to solve this, but the model said, screw you, I'm not going to do it. Or sometimes the model did it, but the modeler said, I'm not going to report this, this is so ridiculous, right? And you see that if you move further and further to the right, there's more and more infeasible solutions. Essentially what the models say here that we cannot solve this problem. Some models, that is because it's physically impossible to meet this target. They simply can't get the physics to behave the way the policy prescription said it should. Some models say we can do this, but the cost would be astronomical. We would have to quadruple the price of energy next year, and then we would assume that it would be a tax revolt, so we're not going to report this. And in some cases, there was also some issues of numerical infeasibility. Why does this matter? This is the target of the European Commission. This is the target of the United Nations, to stabilize around 450 carbon dioxide equivalents in the atmosphere. That would give us roughly a 50-50 chance of meeting our 2 degrees target. A lot of models say, sorry, this can't be done, right? These are the total cost of emission reduction. This is essentially the same picture. This gives you an idea of the effort that is needed to get there. So these are again the free targets. These are the models. What we're looking at, the dots on this axis, is what would emissions in 2050 be relative to what they would have been without climate policy, right? I skipped the graph, which I should not have skipped. I'll go back. Now what you see is that the more stringent the target, the lower the emissions in 2050 should be. That should not surprise you. But here again, we see the same information. These are the models that say, sorry, can't do. And as we move to the right, there's more and more models dropping into that category. The models that can do, importantly, cross the zero line. That is, emissions go negative. How do we do that? There's two ways of doing it. One at the moment is pure fantasy, and the other is almost pure fantasy. At technologies of 2015, right? But we're talking about 2050. Pure fantasy is that we just suck the carbon out of the atmosphere. We build artificial trees that suck carbon out of the atmosphere. Trees know how to do it, so why can't humans make a device that does this? Well, we can actually. Doing this at the required scale is going to take a bit. The other is to go for negative carbon energy, where essentially what you do is instead of venting the CO2 into the atmosphere, you put an additional factory next to your power plant that separates the CO2 from the flue gas and sticks it deep underground, deep underwater. That would give you carbon neutral electricity. If you want to go to negative carbon electricity, then what you need to stick in is not fossil fuels, but biomass. So you would need to grow plants at a fairly massive scale, use that instead of coal and gas to make electricity, and separate the carbon before it enters into the atmosphere and stick it underground. Technically, this is feasible at the moment. We need to do it at such a massive scale that it's hard to imagine that it will ever be feasible. Just to give you an illustration of the scale needed, MIT did some calculations. Because CO2 is less dense than, say, oil, if you want to capture all the carbon that comes out of power generation, the amount of pipelines that you would need to transport the CO2 to safe places to store is 5 times the amount of pipelines that we currently use to transport oil and gas. That's sort of the scale of the infrastructure that you need. And then, of course, you also need to find places to store all that carbon, which may also be a bit of a challenge. But that is what we would need if we want to stay definitely, if you want to stay below 450, in a later assessment, where it's very, very simple, without negative carbon energy, we're not going to get to 2 degrees. Negative carbon energy is not proven technology. And actually, a lot of models say if you want to go to 550 ppm, then you may well need negative carbon energy. One of the reasons, and that's what I should have said before, one of the reasons that these models disagree so much on the cost of greenhouse gas emission reduction is because there is such a wide range of what unregulated emissions would be. And obviously, if you think that without regulations emissions are rather low, then your target is not so stringent, you don't need to work so hard. But if you think that without regulations emissions will be high, then for any given target you need to work much harder. And that is what we see here. This is the range of model projections in the same exercise. Some models say we're going to hit 650 parts per million around the year 2040. Other models say no, not until 2070. And of course, if 650 is your target, then according to these models, that's not a very stringent target. We don't need to work very hard. Whereas these models say, well, that's a very stringent target. We need to work very hard, and therefore the costs are high. So this matters actually quite a bit. Showed you a table of total costs. These are the marginal costs, so essentially the carbon tax we need to apply in the year 2020, given in dollars per ton of CO2. It's not a unit that means a whole lot to you. Dollars per ton of CO2. The euro has been moving quite a bit, right? Here we have $20 per ton of CO2. That must be about 15 euros per ton of CO2. Why do I translate it into euros per ton of CO2? We have this European trading system where emission permits are traded across Europe. At the moment they trade at around 5 to 6 euros per ton of CO2. And that's the number that you should compare it to. So what do we find in this column? Again, the same message, that some models say 20, other models say 2. Again, an order of magnitude uncertainty about what the cost will be at the margin. So that's an important thing to keep in mind. Some models say, well, the current price of carbon in the EU is roughly what we would need if we're heading for this target. Some models say, no, it actually should go up a bit. Other models say it can go down a bit. If you move to more stringent targets, the prices that you see all exceed the current price in the EU. But this is the carbon price in the year 2020. And it's the carbon price full across the world. So what these models tell us that if we want to go to say 450 ppm, then some models say, oh, we can't get there. Other models say, well, in order to get there, what we would need is extend the EU ETS, which currently covers about half of emissions in the EU, to all emissions in the EU. We need to multiply the price by a factor 10 or more. And we need to extend this scheme to all countries in the world. All between now and 2020, if we are aiming for this target. But also if we aim for a less stringent target, or even not very stringent target at all, then that is the task that we have ahead of us. So we should convince the Congress in the US that within the next 5 years they adopt European-style environmental, or rather climate policies. Not very likely. But yeah, we also need to convince the Indians and the Chinese and the Nigerians and the North Koreans to do the same thing. It's perhaps a bit idealistic to think that that would happen, right? And of course, if other countries don't play, that means that those who do care about the climate need to work much harder for the same global target, right? So those are the insights that come out of this. This is a slightly older story. This is about the dynamics of greenhouse gas emission reduction. What you're looking at here are two sets of CO2 concentrations in the atmosphere. There's the dark ones, and then there's the blue ones that are much lighter. And the important thing is that in the long run, they all end up in the same place. So for the climate, it doesn't really matter which one whether you go for the black one or the blue one. They all end up in roughly the same place. These are the corresponding emissions. And the difference between the light blue and the corresponding black one is that you deviate much later from the unregulated scenario. In the blue ones, you start aggressive climate policy immediately. In the black dotted ones, you start aggressive, you postpone aggressive climate policy, you start preparations now. Because you end up in the same place, that does mean that in the longer run, you have to work harder. Okay, so those are the two scenarios that we're looking at, and then if you want to understand what does this do to costs, you need to compare this bar to this bar, this bar to this bar, this bar to this bar, and what you see is that if you postpone ambitious climate policy, then you save a lot of costs. According to some models, that is 10%, but it's 10% of 20 trillion, so that's a tidy sum of money, right? According to other models, it's more like that you can save 2/3 almost of the cost. So that's saving worth making. Now, why do the models say this? There's 4 reasons why you would want to start slow with climate policy and accelerate rather than go in with a big bang. And the first one is capital stock turnover. The machinery that we use to convert fossil fuels into electricity or petrol into motion or gas into heat is all long-lived. Cars have a lifetime on our roads of about 10 years. Power plants have a lifetime of about 40 years to sometimes 60 years. And that means that the machinery that we currently have, the infrastructure that we currently have, is sort of optimized for a world where there was no climate policy. So if we now all of a sudden impose a very high carbon tax, essentially we destroy capital. This infrastructure that would have had a useful economic lifetime of 10, 20, 30 years, all of a sudden becomes obsolete. And we destroy capital and we have to invest a lot in replacing it. That's one scenario. Or we just have a lot of capital that is sitting there and not making the profits, and therefore there is a high loss. And some of these processes take a very long time to change, right? One of the implications of a strengthened climate policy is that people move closer to where they work or where they study. Now, that people don't decide to move overnight. That takes a long time. If you have a young family, that may take a decade or more before you have the next opportunity to move. And that means that during that period, you're essentially paying a high carbon tax, a penalty on a decision you made innocently, not anticipating climate policy a long time ago. And you're just paying that penalty. Doesn't reduce any emissions because you don't change your behavior, you're not moving. But you do pay the cost, right? So for those reasons, it makes much more sense to start with a low carbon tax, ramp it up over time, and give people the opportunity to readjust their investments based on the anticipated future price of carbon, rather than punish people for decisions they made in the past, assuming that the carbon price is zero or very low. That is one reason, and a very important reason, why starting slow and accelerating is less costly. Second reason is technological progress. As I've said a couple of times now, at the moment, renewable energies are a lot more expensive than fossil fuels. The price of fossil fuels has been falling over the last couple of years. The price of renewables has been falling over a much longer period. And the expectation is that renewables will start to compete with fossil fuels over the next few decades without subsidies, right? That means that if you now replace fossil fuels with renewables, you pay a penalty on the price. If you wait 20 years, if you wait 30 years, then you will have cheap solar, solar that is a lot cheaper than it is now, and the penalty will be less. So if we think that technological progress favors renewables, as most people do, then waiting pays off. The third reason is discount rate. We care less about the future than we care about today. That takes down the cost because essentially postponing the cost into the future. So that is an important reason. And the fourth reason is very similar. Carbon dioxide, only a part of carbon dioxide stays in the atmosphere forever. Most of it is degraded. And that means that if you have a target for a concentration of CO2 in the atmosphere in the year 2100, then emission reductions in the year 2090 contribute more to that target than emission reductions you do now. Because emissions avoided now also be degraded. Right? So the cycle also acts as a discount rate on the future. That's the fourth reason to start slow and accelerate. It's another message that goes down very well with politicians, right? Because you need to save the world before you get re-elected. But it is probably the best policy. Here, politics and policy are in clear conflict. Okay, 15 more minutes for what is perhaps the most difficult bit of this lecture. I talked a little bit about the confusion that some people have where they say, well, sort of the market rate of energy efficiency improvement is really because of policy. I joked about George Bush announcing 10% improvement in energy efficiency over the next decades, not realizing that in the previous 3 decades energy efficiency had improved by 18%. I may have made snide remarks about engineers claiming that we're wasting roughly 30% of our energy and therefore we can cut our emissions by 30% without cost. Those are just remarks made last of ignorance. But there's also an economic case for reducing emissions while stimulating the economy. The models that I showed earlier, or the model results that I showed earlier, are all optimization models or models that assume a perfect market equilibrium, and often also a dynamic equilibrium. And if in these models you impose a new policy, then there is necessarily a cost. Again, it's very intuitive. These models, their starting point is that they're in the optimum. And if you're in the optimum, the only way forward is necessarily a cost. If you climb mountains or walk hills, that if you're at the top of the hill, that's your starting point, then the only way is down. And if your assumption is that you're at the top of the hill, then whatever you do, you go down, right? This is not the case if you have a model with prior distortions in. If the starting point is an imperfect market or a market that is distorted by policy, then you're somewhere at the side of the hill, and depending whether you go north or south, you may go up or down. If you're at the top of the hill, the only way is down. If you're somewhere at the hill, you can go either way. And in the most abstract way of putting this, if you can design a climate policy such that you reduce the initial imperfections in the economy or the initial distortions of the economy, then you gain something, right? So climate policy in itself will impose a cost because energy will become more expensive. But if by doing so you reduce the distortions in the economy, then that's a gain. And then we're in a situation where we have a loss and a gain. We don't know which of the two is bigger, and we may actually be lucky that we're reducing emissions while stimulating the economy. And the crucial word here is that we need to reduce the distortionality of the fiscal system. Now, how can we do that? First, we need to understand what is distortion, the distortionality of the fiscal system. So, the starting point is a market equilibrium without any government intervention, right? So what do we do if the government raises money, imposes taxes? They typically change behavior, right? So if we impose a tax on labor, we essentially induce people to work less and have more leisure. If we impose a tax on profits, then essentially we encourage companies to invest less. We change the behavior of our economic agents. And if their starting point was that they were in an optimum, by changing their behavior, we're moving them away from how they otherwise would have behaved. They consume less, they invest less, the economy grows less fast. And essentially the distortion of an economy, the measure of distortion is people's behavior with tax versus people's behavior without the tax. Now, if you take that, then you would find that if the tax base is narrower, then you would be more distortionary. Because for every £1,000,000 raised, if fewer people pay that tax, the tax base is narrower, you would distort their behavior more because the unit tax, the tax rate, must be higher. Because the fewer amount of people pay the same total in tax. Tax is also more distortionary if price elasticities are higher. And obvious, if price elasticity is higher, then people respond more strongly to a change in the price, and of course the tax induces a change in the price. So in those cases, you would find a greater distortion. And the third reason that is not listed here, sorry about that, is that if the initial tax is higher and you raise the tax, then also you will be more distortionary. And the rule of thumb there is roughly that the cost of a tax raise is quadratic in the original tax, the level of the original tax. So, starting from that point, if we reduce greenhouse gas emissions by imposing a carbon tax, then the government has additional tax revenue. If that tax revenue is used to reduce labor taxes, we gain something, right? The initial point of the carbon tax is roughly 0. The initial point of the labor tax is fairly high. So reducing the carbon tax by a little bit does not cost a whole lot, but reducing the labor tax by a little bit brings a lot of benefits, right? That's the main reason, and that's one I'm cross with myself, that's not on the slide. That is the main reason why shifting taxes from labor towards carbon would probably bring an overall reduction in the distortionality of the fiscal system would actually bring an economic gain. Everybody uses energy, so the tax base is actually fairly wide for carbon taxes. Only 40%, I think, of people in the UK work. So labor taxes fall on a narrower base. In both cases, the price elasticity is actually pretty low. So labor is fairly regulated, and labor contracts come lumpy. So a decrease in the labor tax would actually not lead to a large increase in labor supply. And similarly, an increase in the carbon tax would not, in the price of energy, would actually not lead to an immediate reduction in the use of energy because of capital stock and so on and so forth. So based on first principles, right, we can expect that if we shift the tax burden away from labor towards carbon, then we would actually see an economic gain. And that is what we see in this graph, where people try this and try to quantify this. A lot of information here. This is essentially the cost, where here we see, it's called welfare variation. So below the zero are costs of climate policy. Above the line are benefits of climate policy. And the assumption here is we impose a carbon tax, we use the money wisely, we spend it on a reduction in payroll taxes in Europe. See, the different models have the different different assessments of how much benefit this would bring. You would see that in different countries, you would see different benefits. But actually, the majority of results say, well, this is at least possible in theory, right? The exact effect depends on exactly how the tax is levied. That's the two purples that you see here, but also depends on what do you assume about the labor market. Is it sort of like our standard perfect labor market, or does the labor market have some distortions as well? That's the dark purple versus the light purple. So again, you cannot just say the answer is 7, right? You need to actually look at a lot of detail before you get to what is a credible estimate. Of course, it matters what you do. With the revenue, that's actually better shown on this. The previous results were all for the EU. These are results for the US. 4 different models, levying a carbon tax. Here you see the carbon tax, and using the revenue for different purposes. And depending on the purpose, you see actually that the economic results are different. So what do we see for the US? In the first scenarios, the carbon tax revenue is used to send everybody a check in the post, lump sum recycling. In this case, the money is spent by the government. The revenue is used to increase government consumption. This is a reduction on the income tax. This is a reduction on the tax on profits. You see there's a sharp difference there in results that is also carried with the other models. These are payroll taxes. And here the money is used for investment credit. So what you see here is, yes, it makes a lot of difference what the government decides to do with the carbon tax revenue. No surprises there. But there's also a difference between the US and the EU. Because this scenario we looked at previously for the EU, and in the EU, labor taxes are high and profit taxes are low. So if you have carbon tax revenue, you would go after the labor taxes. In the US, it's the other way around. Income taxes are low, corporation taxes, profit taxes are high. So there the economic benefit is actually in reducing the corporate tax rather than the personal tax. This leads me to my final point. So yes, it is possible to reduce greenhouse gas emissions and make money at the same time. But what you need to do is you need to raise money through a carbon tax, and you need to spend the money wisely. And spending the money wisely depends on circumstances. You actually saw that different models will give you different results. So you need, as a politician, to have a good understanding of how does my economy work and what does my fiscal system do to the economy. And not everybody in Parliament has a PhD in economics, right? So most parliamentarians would actually not understand the subtle differences there. But also, as a politician, you need to resist the temptation to spend the money foolishly. Say, to reward your political allies or the people who voted for you, or seduce the people who might vote for you in the next election. That is not how you should spend the money. You should spend the money on that tax that we all agree is the most distortionary. So politically, economically, yes, you can come up with a scenario where you reduce greenhouse gas emissions and make money. Politically, it's actually hard to imagine that all the conditions for that would be met. Okay, that was it for now. This afternoon there's a seminar, and we're going to take you through the exercises. Okay?